PARP1 in neurodegenerative diseases. Welcome back to our channel. Today, we're diving into the fascinating world of neurodegenerative diseases and the pivotal role of an enzyme called PARP1. If you've ever wondered how conditions like ALS, Alzheimer's, and Parkinson's disease are connected, you're in the right place. So, grab a snack, sit back, and let's get started. First off, what is PARP1? PARP1, or poly-adiporibose polymerase 1, is an enzyme that plays a crucial role in repairing DNA damage. But in the context of neurodegenerative diseases, it can also contribute to cell death and neurotoxicity. Let's break down how this happens in various conditions. Let's start with amyotrophic lateral sclerosis, or ALS. This is a progressive disease that affects motor neurons, leading to muscle weakness and atrophy. Interestingly, about 90% of sporadic ALS cases show overexpression of PARP1. This overexpression is linked to the release of a protein called apoptosis-inducing factor, or AIF, from the mitochondria, which can trigger cell death. In ALS, proteins like TDP-43 and various RNA-binding proteins accumulate abnormally. TDP-43, in particular, is significant because it mediates neurotoxicity in the spinal cord. When PARP1 is overactivated, it affects TDP-43's function, leading to further neuronal damage. Now, let's talk about multiple sclerosis, or MS. This autoimmune disease is characterized by the demyelination of neurons. PARP1 activation in MS is triggered by oxidative stress and DNA damage, which can lead to energy depletion and worsen neurodegeneration. Moving on to Huntington's disease, a hereditary disorder caused by CAG repeat expansions in the Huntington gene. This leads to the production of polyglutamine, which can generate reactive oxygen species, or ROS. Elevated PARP1 levels are associated with the accumulation of the mutant Huntington protein, contributing to neuronal dysfunction. Excessive PARP1 activation can deplete NAD+ stores, leading to energy failure and a specific type of cell death known as parthenotos. Now, let's shift gears to Alzheimer's disease, or AD. This condition is marked by the accumulation of amyloid beta, or A-beta, which forms plaques in the brain. A-beta is derived from a larger protein called amyloid precursor protein, or AP, and its aggregation is particularly harmful to neurons. A-beta can activate enzymes that produce free radicals, leading to DNA damage. This damage triggers PARP1 to go into overdrive, trying to repair the harm. However, this overactivation depletes NAD+, causing energy crises and ultimately contributing to cognitive decline. Next up is Parkinson's disease, or PD. Here, the main player is alpha-synuclein, a protein that forms Lewy bodies in the brains of patients. When alpha-synuclein is modified by PARP1, it tends to mislocalize to the cytoplasm, leading to oxidative stress and neuronal damage. This creates a vicious cycle where more alpha-synuclein accumulates, further activating PARP1 and depleting energy resources. Interestingly, elevated levels of PAR in the cerebrospinal fluid of PD patients could serve as a biomarker for the disease, highlighting PARP1's role in neurodegeneration. Inhibiting PARP1 has shown promise in enhancing autophagy, which could help reduce alpha-synuclein accumulation and prevent neurodegeneration. In summary, PARP1 is a double-edged sword in the context of neurodegenerative diseases. While it plays a vital role in DNA repair, its overactivation can lead to severe consequences, including neuronal death and cognitive decline. Understanding this balance is crucial for developing potential therapies for diseases like ALS, MS, Huntington's, Alzheimer's, and Parkinson's. If you found this information helpful, don't forget to give us a thumbs up, subscribe for more content, and share your thoughts in the comments below. What topics would you like us to cover next? Until next time, stay curious and keep learning.
Pharma